the major difference between the kind of system we derive here and what we could derive from either finite element or finite volume, from finite difference or finite volume, is this additional mass matrix that appears on the left-hand side, right? If you write the equation down in vector form, you would have this M being a matrix times du dt. So just a note here is that U is a column vector, right? U is a column vector. So du dt is a column vector. M times du dt is basically this matrix vector multiplication. That's basically writing this summation in a shorthand. Is equal to, again, there is a summation here that can be written as a matrix vector product, A times U. That's what we have used to solve the matrix system last time, right? Plus B as another column vector. So this is the kind of equation you would solve with an ODE solver, right? And normally, you would have to actually invert this mass matrix and write down du dt. If you use, let's say, ODE45 for any given ODE solvers, you have to write this down like that. You have to multiply M inverse on both sides of the equation to get this kind of equations. And then you can plug into an ODE solver. So this additional M inverse here is actually a little bit unique in finite elements, because usually when you apply an ODE solver, if you do forward Euler, right, and if you unless you want to use an implicit scheme, if you use an explicit scheme like forward Euler or even a Runge-Carter scheme, you never have to invert any matrices. And only when you solve ODE using implicit schemes, you would have to invert matrices. Well, allow me to take a little bit interruption of our midterm again. I think in more than one occasions, one of you have chosen values of A and B to make my solver break. And the way you made my solver break, I think, do anybody remember what values of A and B you used to make my solver one break? You have like, I think more than one of you had witnessed when you choose particular combinations of A, B, and delta T, you saw like a matrix being singular or something like that. Anybody remember? Yes, no? I know at least the two of you have seen something like that in the midterm, right? Yeah. Okay, so if I recall, it's actually A has to be positive. It's something like 1 or 2. I think maybe 10. Let me try this. 10. No, actually, A is actually no. So A is equal to 0, B equal to 10, and 0.1. Let's try this. Does it work? Yes, right, something like this. So basically, you've chosen values of A and B and delta T so that the matrix I have to invert is exactly singular. Okay, so one thing you actually could learn from that is that this solver 1, is an implicit scheme, right? If you look at what line 8 does, it's inverting a matrix. See the backslash over here. Okay, so when you have to invert a matrix, it is going to be an implicit scheme. If you look at forward Euler, for example, I never have to invert a matrix. The matrix is multiplied on the previous solution, but I never have to invert it, right? For example, if you look at solver 3 is actually trapezoidal rule, another implicit scheme. Again, I have to invert a matrix. See the backslash here. So in linear algebra, inverting a matrix or solving a linear system is actually a lot more expensive, especially for large matrices, a lot more expensive than matrix multiplication. Okay, Yeah, matrix multiplication. Multiplying a matrix with a vector is it takes order of n squared operations, where n is the number of rows and columns of the matrix. While solving a linear system with an n by n matrix, you have to spend on the order of n cubed operations. So the difference is really large if n is huge, right? If you have a partial differential equation, like what we have been discussing here, if you are discretizing, let's say, a partial differential equation with 10,000 degrees of freedom, so the M is a 10,000 by 10,000 matrix, having to invert the matrix here or not really makes a huge difference. So this is actually one of the reasons when you are solving, when you have to use finite elements, a lot of people choose to use an implicit method for time integration because you have to actually invert matrices anyway. And choosing an implicit time integration scheme actually wouldn't actually cost you anything more than an explicit time integration scheme, right? Because you have to invert a matrix anyway, so why don't you use an implicit scheme to gain all the advantages of stability and being able to deal with stiff systems and things like that. Okay, so this is really the kind of equations, well, this kind of equations that we ended up deriving if we use finite elements for an unsteady PDE.